Welcome, everyone. Hope you guys are enjoying your nights. Welcome to our session on building new gameplay features with Runtime AI and Sentis. My name is Bill, and I'm a product manager in our AI group. And I've got Alex with me, who's our lead engineer on Sentis, and actually some customers with us that are going to be doing some demos with us. We were just remarking how awesome it is that a bunch of the people we've been working with over the past year and a half are in the audience, so thanks so much for coming. Let's jump in. So what we're going to do is do kind of a product overview of Sentis for those who are not familiar and kind of get you familiar with how the product works. We're going to jump into some technical demos that break down real use cases that game developers are doing and then wrap up. And we will have some time for questions. Okay, so let's jump into the product overview. So let's say you want to create some realistic lip-synced animations on this little coyote here. So there's kind of two traditional ways you might do this. You could do phoneme detection, where you kind of associate word phonemes with some very genericized animations. The only problem is you can't really get some unique emotion. The other way you can do it is with mocap, right? Motion capture. You have to kind of pre-record everything, which can be great. It can give you high fidelity, but it's not dynamic, right? You can't adjust to new words. So what if you could do best of both worlds? So this is actually a really good problem to be solved by a neural network. And let's show a live demo of this right now. So I'm going to launch this Unity app that uses a neural network to hallucinate the lip animations. And it's going to be a live demo with my voice. So we're going to turn up the computer audio. Okay, here we go. Let's make this coyote talk. I'm a big bad wolf. I'm a big bad wolf. Come into my cabin. Come into my cabin. Back to the presentation. Okay, cool. So you can see that it works. So how do we do this? So we're using Sentis for real-time neural network inference on the local machine, right? We're not doing a cloud inference. It's running on the PC. And Sentis is basically this new engine component. By the way, we just released it to production 2 weeks ago, so it's fully usable. It's not in experimental anymore. And what it does is basically a function approximation. So the neural network here will take in the audio file, and the neural network will process the audio file and output some face animation. And you can do this to solve lots of problems in your games. So the basic workflow is you need to get a model. You need to get it in Unity. You can hopefully run it really fast and then deploy your game like you normally would. So let's take a look at how you might do this without Sentis and see kind of why we actually built this framework. So what about a cloud server inference, right? Everyone's using ChatGPT. Can't you just run this kind of inference on the cloud? Well, you can't really get the cloud into Unity, into your app. That doesn't really work. Obviously, you could do web requests. That could work. You have to set up a server, so maybe it'll work. Next step, make it fast. This is where you run into a real issue, right? Network latency on this kind of inference would be probably at least a couple seconds. So you're going to be way behind real time with the lip sync. But obviously, if you need to run like a really large model, like a large language model or a generative model like Stable Diffusion, you probably want to do that in the cloud. And then lastly, you could deploy the game with a cloud inference, but you have to have some cloud costs from the infrastructure there. Okay, local Python server, that's the other main option. Get it into Unity? Not really. You can't run Python natively in Unity out of the box. Can you run it fast? Maybe, but it's not really integrated with the Unity system, so you can't tune it. If you wanted to deploy this, I mean, technically you could, but you have to have your users have a Python interpreter. Like, come on, this is crazy. You're not going to do that. So, hint, blue is good. So, so with Sentis, we kind of solve all these problems, right? On the get a model part, we actually have an integration with Hugging Face, so you can go there and get pre-trained models that are converted to our Sentis format. You can drop them right into your game. We even have internal people at Unity that aren't developers do this, so you can definitely do it. You can also train models with a tool called ML Agents for reinforcement learning models, which, by the way, we're updating shortly to work with Sentis. Next step, getting into Unity. So you drop a ONNX file into Unity, and we automatically convert it to our representation. And it's treated just like any other Unity project asset, and we automatically optimize it. We fuse some layers, we do some black magic, and we get it to run really fast. For making it fast, it's really good at really small niche, like feature-specific models. It's not good, like I said before, for some really large LLM or generative model. Although in the future, we are seeing quantized LLMs and other kind of performance tricks. I think in 2 years-ish, you're going to be able to run some of these LLMs locally. And then lastly, for deploying, you just deploy it like any other build. There's no change. It's still build once, deploy everywhere. Okay, so let's look at how we did this for the Coyote example. So this is a speech kind of encoder decoder model. It's the same one if you saw our Orb demo last summer. It's using the same one. It's called Hubert. It's trained on like a huge mass of audio from the internet. So it works by taking the audio and doing a waveform embedding on the audio, and then outputs the decoder to generate the lip animations. Bringing it into Unity is obviously easy, like I just mentioned. And we send the audio, we get back the skinned mesh renderer blend shapes. And then what do you after that? You always obviously test performance. So on our first build of this demo, it was like kind of hitching a little bit. We couldn't get 30 FPS. So luckily we shipped Sentis with a bunch of interesting tools that allow you to tune it. And so in this case, we just split the inference over a couple of frames, and then it runs at a really nice frame rate. And then of course we can build it. And it works on mobile, works on web GPU, any runtime platform. So now you get a taste of a really simple example with Sentis. I'm super excited to show you this next thing, which is a sizzle reel of 17 projects from developers all over the world. We've been working with thousands of developers trying out Sentis. And so this is the first time this is being showed, and some of the folks in the room are in this video. So thanks for all your hard work.
Cybernetic mazes, let me be your muse.
Let's do a round of applause for all the developers. Awesome. Okay, so now we're going to take 6 of those demos that you just saw and break them down kind of like the Coyote in more detail so you can really see how these use cases came to life. Okay, so we have these 3 categories just like the video: real-world interactions, smarter gameplay, and the game effects. And my favorite category is the real-world interactions, so we're going to do the most there whether you like it or not. Okay, so the first one is called Bionic Vision. So there are actually 50 million fully blind people in the world, and about double that have some sort of significant seeing or vision deficiency. So there are these guys at University of California, Santa Barbara, in this Bionic Vision lab trying to work on improving vision for those people. And so what they do is There's all these implants out there powered by electrodes, and they stimulate the brain. And what they're trying to do is make those implants better to kind of create some visual impulse for blind people. So what they want to do is simulate what blind people see for sighted people so that the sighted researchers can do a much better job iterating on the implants. And they wanted to make that really immersive in real time so that you can see the whole world anywhere you are, just like a blind person. The trouble is this is very computationally expensive to do the simulation. So how can they solve this with a neural network? So this is the basic setup for a blind person with a electrode implant. They have some glasses. They don't see anything out of the glasses, obviously, but there's a camera between the eyes, and it takes in frames from the real world. Okay, so some input, like they see a stop sign, and this visual processing unit, what it does is it processes that signal, and it does a like field of view reduction on it because the electrode field of view is actually quite small. It's like 5 or 6 degrees. And then it creates an impulse in the electrode that represents this frame. And then that creates some output projection, which for some of you might be the first time you're seeing what blind people with electrodes see of the real world. If you can't tell, that's the ST of the stop sign. So how can we make this all better? So this is a view of like a dangerous situation for a blind person, and this is actually what today's kind of implant technology looks like for that blind person. And now sighted users, sighted researchers can see the same exact thing. So they can walk around with a VR headset and go anywhere and see what any environment looks like for these patients. And the amazing thing about that is that now with this new capability, we think we can get to somewhere in the middle, which is a much, much better implant for blind users in the future. I don't know when it will be that good, but one day, hopefully. The other thing they can do here is, which they're working on right now, is do some object detection on the scene. And since it's running the camera frames and using Sentis for inference, they can add all these modalities of inference, right? So they can detect a car or a person. They can do some scene simplification or increase the contrast on those detected objects and then make the prosthetic vision even better. So overall, this model is like an image-to-image convolutional neural network that the researcher Opperv wrote. It takes in the camera view, runs the model, and then generates the hallucinated processed view. The model is super performant. They were actually longtime Barracuda users before Barracuda became Sentis. And they had to simplify their models dramatically because Barracuda didn't work quite as well. But now they can run their full model, and they can run it on a huge number of electrodes, like thousands of electrodes. It's about 100 megabytes, and they can get it running in the HTC Vive headset at 90 FPS. So super performant. So super cool to see this, and we're going to jump on to the next demonstration. And I want to introduce Hector, if you want to come over. He's going to demonstrate Magico Mirror. And Hector is a local Barcelona resident. He has a company called Tetravol, which is an innovation and XR studio just down the street. And he's going to tell you about a really, really cool project. Here you go, Hector.
Thanks a lot, Bill. Okay, wouldn't it be great if we could create apps and games that understood our hand gestures and our facial expressions? This is what we are working on. Let me show you. If we could make our apps understand our hand gestures and facial expressions, then we could do things like this. We could control and pick up objects just by waving our hands. Or we could control in real time an avatar. We could make the avatar come to life with our own facial expressions and even customize it if you want. Or we could do a showcase of a product. We could showcase an object, move it around, rotate it, scale it, and controlling it in real time just with our gestures. This is what Unity Sentis makes possible, and let me tell you, it's awesome. Back to the presentation. Okay, so Magico Mirror is a series of installations that our company, Tetravol, has made for several clients, like Mobile World Capital or the Madrid Airport here in Spain. And this is the latest installation that we have made for here in Barcelona, for l'Aquarium de Barcelona. And it's an interactive installation which has 2 games. The first game runs on tablets. We have 6 Android tablets where children and adults as well, they can pick up fish and then they can paint them as they want. And once the kid has finished painting his or her fish, it comes to life and then goes to a bigger screen where we are simulating a coral reef. And then on the center screen, we have this Magico Mirror installation where the kid is playing to clean the ocean. And as you can see, it works like a magic mirror where the kid can see lots of objects and this garbage that he needs to eliminate. And then he gets this crown as a reward. Okay, so these kinds of installations have worked very well, but they have their limitations. They work on Microsoft Kinect. And Microsoft Kinect is a depth sensor that has a lot of features and a lot of possibilities, but it has several issues. First of all, it requires an expensive depth sensor, and also it requires a high-end PC with Windows, which makes it only available on this platform. You cannot run it on any other. Also, it has a problem. It has very limited hand and face tracking. So if you want to capture the subtleties of the facial expression or finger positions, it's not possible. And most importantly, it has been discontinued by Microsoft. So you can use it, but it's becoming more obsolete as time goes by. And besides that, we really wanted to make these kind of installations easier and more affordable for our clients. So we want to use, instead of a PC-based Kinect solution, use just a webcam with an Android device. And this is exactly what Sentis makes possible. And in this case, we are using the Blaze family models from Google MediaPipe. And in this case, it has been very easy for us, thanks a lot to the Unity team, because they have converted these neural networks to work with Sentis inside of Unity. And it has been very straightforward to us to just get these models, as you can download them on Hugging Face, and make them work and focus on the gameplay. Okay, so let me show you how the pipeline works. Basically, what you do is you take the input image that comes from your webcam, and then you run this input image through a first neural network, which is the detector model. The detector model then detects the body, in this case, and detects its orientation and size. Then we create an affine transform to run a second model, which will be giving this second transformed and cropped and rotated image so that the model is properly centered and upright. And then we run the second model, the landmark model. This is the one that will detect the skeleton. And then finally, we run the transform backwards, and we reorient the landmarks to perfectly match the input image. Okay, so this is the process. Now, a couple of comments on this process. These neural networks, they run on very low resolution inputs. We are talking about from 192 to 256 pixels wide. So it's very important that we run the detector on one image, but for the second landmark model, we need to go to the original image and crop from that to avoid lowering resolution and bad performance. And another thing that we can do to improve even more performance is to run the detector only on the first frame, or only when we lose track of a body. And then we can just use the landmarks model, and as it moves on the input screen, we can just use the information from the landmark model to recrop the image. Okay, regarding performance, it's blazingly fast. And I must say, it has improved a lot over the months. The work that they have been doing is great. And on a PC, it works with such performance that we can achieve 30 frames per second for a full inference on body, hand, and face by using the light models from the Google MediaPipe family. If you want to have a better detection, you can use, instead of the light models, heavier models. Or if you want, you can run this same simulation on Android as well. Then you will get a lower frame rate, longer inference times. But here is where the asynchronous capabilities of Unity 6 kick in. You can completely decouple the rendering frame rate from the inference frame rate. So you can have consistent 60 frames per second while having the inference running on an asynchronous mode, and it works perfect. Okay, let me show you before that, sorry. I wanted to show you the detector model in the real-time demo. Here you can see this, this model as in real time, as it's detecting my face and hands. And I wanted to show you this cropping that we are doing with the image. Here on your top left, you can see the detector model at work. You can see that it's detecting my face right now. And then you can see on the right the landmark model running on the cropped version of this image. And then, as I showed the model my hands, you can see the same cropping in real time applied to my hands as well, okay? And a very important thing to note here is that it also works with WebGL, with WebGPU. So you can run it on the browser and do the inference on the local compute of the user's device. Okay, so I hope you have enjoyed this little presentation, as Bill and Alex have enjoyed in the aquarium. By the way, for the ones here in the room, you are all invited. If you have time while you are here in Barcelona, it would be an honor for me to come with you to L'Aquarium Barcelona and let you see the experience yourselves. Thanks a lot, and back to Alex.
Yeah, really go. It's really cool. All right, so let's keep it with tracking your body over time, but now let's go more into VR and look at what you can do on the Quest with similar methods. All right, so here we're presenting the work of Ben and Sebastian Stark, a longtime Sentis and Barracuda user. But for this, it's their presentation at SIGGRAPH that they presented this year, and it's all open source on GitHub, so if you like it, go ahead, download it, and play with it. Sorry. All right, so here's the problem you want to solve. So now you don't have a webcam. You're in VR. So you have the Quest, you have some controllers, and the player is moving around, maybe playing Beat Saber, moving around. So you're tracking the headset, and the controller. But that only gives you some very sparse input. You only have the hands and maybe the head. But you want to be a really immersive game and simulate the whole body of the character moving around and being cohesive with what the player is doing. So what you want to do, you want to be generating the full body animation of the character alongside their real movement. Of course, this is running on the Quest, right? So the hardware is pretty limited. And if your frame rate is very low, it's going to cause motion sickness and all that. So you really need to have a really smooth FPS and very high performance. So let's take a look at what they did.
Translating motions from a real user onto a virtual embodied avatar is a key challenge for character animation in the metaverse. We present a generative framework that learns mapping from sparse user inputs to high-fidelity avatar movements while preserving the original motion context of the user. Our codebook matching technique enables learning both the motion manifold as well as how to sample the motions from discrete probabilities in an end-to-end manner. Beyond typical 3-point tracking setups, our method supports optional joystick or button inputs and can produce diverse embodied avatar motions accurately, realistically, and with zero delay.
Pretty cool, right? All right, so how does it work? All right, so it's state-of-the-art, latest research, so it has a lot of steps, but we'll go into details and explain all of them. So it's a 4-step process. So you see, you start from the sensor input, and then again, you apply all the steps, and then you get the full animation. All right, so step 1. So the cool thing is you have the sensor, so you have some tracking of the user. You only have the upper body because you have the hands and the face. Generally, you're moving in upper motion. What we're going to do is we're going to run these sparse input through a first neural network, and the first network will give you the upper body animation sequence. So you'll take that, run through the network, and it will generate the additional joints, that may be like the other joints of the upper body of the character. The important thing here is that, yes, you're moving around, but the player is also clicking on buttons. So if you want to jump, if you want to shoot, if you want to roll or do something like this, it's additional button presses. So for that, that also goes into the model, but that drives the root motion trajectory. So if you're jumping, you're not doing a jumping animation, the root is also moving up. So you want that to be simulated by the model. All right, so step 2 is you want to generate the lower body of the model, of the character. So they're using an autoregressive codebook matching, so that's a fancy like research terms. But what it means is you're using the previous frame, running that through a neural network and generating the most likely next frame that matches the previous one. The codebook matching is actually a very innovative technique. Is before, instead of running it just trying to figure out any animation, you're trying to match what the player is moving, and you're trying to match that to something that you've seen in your training set. So match that to the closest animation you've seen in your training set. That has 2 advantages. One, the motion is very smooth because you're not generating a random motion, you're generating something that you've learned, something that an artist has crafted, so it's very smooth. The other advantage is you're saving computational costs. So you're matching to, in the codebook, to an animation. So if you want a very like high fidelity animation, you increase the size of the codebook, you have more animation to sample from, everything is good. But if your frame rate hitches down, you can lower the codebook size, and now you're only picking from 2 or 3 animations, so your performance is really good. All right, so now we've got the upper body, we've got the lower body. It's time to mix and match together to get the full body animation. So here you have a few options at your disposal depending on your budget. You could, of course, linearly blend between the 2 to get the full body. That works. If you want to be really precise, remember you're tracking the headset and the hands, so you might want to make those really stick to the real position and then run inverse kinematic to kind of get the full body to match a little bit your input IMUs. Or you could also be more fancy if you want. You can have a third model, take in the 2 inputs and generate the full animation. All right, so let's recap a little bit. So you see, there's been dancing and playing the game. The inputs is really the 3 points from the IMUs, so the headset plus the controllers. And the output is the embodied character motion on the right. It's able to compress around 100 gigabytes of animation to a very small model of around 30 megabytes. And the performance is really good. It's around 3 milliseconds on the Quest. So it's 90 FPS all the way. Pretty great. Of course, it's just computer science. It's not magic. If you're crossing the legs like this, you have no sensor. You have no way to know that the player is crossing their legs. So in this case, it'll just try to guess and make something plausible. All right, cool. Let's move on to game animation. All right, so smarter gameplay. Everybody likes that. So when you create a board game, you need to put a bot in it. You need to play an opponent, right? And that's really hard. Also, you need to program it. It takes a while. You need to get things right. But also, it's really hard to get it to feel right, to get the gameplay to be fun. I mean, we've all played games where we play the single player mode and it kind of sucks. It's not very fun. And then you move to the multiplayer. So if you want to do things good, it's really hard. But can AI help come to the rescue and make your AI bots more smart? This is exactly what Nomtech did. They're actually in the crowd. And what they did is they took a little small reinforcement learning model, and the model has been trained, it's self-play, so it plays against itself. And then it's able to, from the current game board, it's able to predict the best possible move. And with that, you can actually now use it to play the opponents or to help the player figure out what's the next move. All right, so this is when your producer comes and says like, wait, we're doing boss, but we're a multiplayer game. Why do we care? But actually, even if you're doing a multiplayer game, your connection might jump and your player might go offline. You might not have enough players and whatnot. So even if you're a multiplayer, you need some bots to play your game. So it's still useful. All right, so let's take a look in action. All right, so first you select your difficulty. Of course, the difficulty will be the model, same model, but if the difficulty is higher, the model will take the best possible moves, like the 10%. You can also tune your difficulty curve depending on how you want your gameplay to be fun. You can see here you've got a little magic wand. Oh, is it over? Oh no, it's playing. So you've got a little magic wand that you can hint the player and tell them, okay, what's the best move? Maybe it's to fold or to bet more. Also, if they did the right move, the best move, you can like give them a prompt saying, "Oh, you did the good move," or if they did the bad move, you say, "Oh, you suck. You did the wrong move. Play again better." All right, and then they play, and then they win the game, and that was not a multiplayer; it was playing against some bots. They didn't know because the bot difficulty matches their play style and their play level, so it was pretty smooth. All right, so the model is pretty familiar. It's pretty small and it's pretty straightforward. If you've heard of AlphaGo, it's very similar. The model ingests in all the board states. So instead, like for poker, is the cards in play, maybe the cash that everybody has, how long you've been in the game. It takes all that. Then the model will produce a probability for all the possible moves and rank them about how likely they are to win the game. Maybe folding this turn will, you might not win this turn, but you might win overall the whole game. So it might have a high probability of winning. If you want to bet, the problem with betting, is you need to be cash weighted. So if you bet $1,000, whereas $10, it might be too risky or not risky. So it ranks all these moves. And then for the gameplay feedback, we can use those probability to drive the gameplay feedback. So of course you can use this model to play the boss, really fine tune your difficulty curve. Or you can taunt the player if they did the bad move. So how do we know they did the bad move? Well, maybe they picked the 10% winning move. So in that case, they're not very good. So you taunt them. All right, so the solution, to summarize, they took a model online in Python. It's all open source. It's called PyPoker. It's a reinforcement learning. It self-plays against itself and then gets a good understanding of the game rules. The inputs is the card on hand, the cash in everybody's table. And the outputs is the most probable hand to win. Of course, this is cash weighted. They didn't use ML agents, but you can. So you could craft your game in Unity, run ML agents, now that it works with Sentis 2.0. And then you could train it locally, and then you could have your small RL model be runnable. The performance size is 3 megabytes. It's pretty cheap. The inference on mobile was pretty heavy, 32 milliseconds. It's a full frame. It's pretty heavy. However, in this case, with the model slicing that Bill mentioned at the beginning, you can get away with it. You don't need to be running that inference like every single frame at 60 hertz, right? It doesn't make any sense. In this case, you can afford to wait a little bit. Maybe you hide it with some particles, with some gameplay. So you'll slice the inference, in their case, about 1 or 2 frames, and then you'll get the result back. The only thing you care is that your frame rate is within budget. You get the result in a few seconds. It's all right. Everything's good. All right, that was it. Hope you like it. All right, so for the next one, I'd like to introduce Josh Loveridge from Stratton, and they use Sentis to help them make their game much faster.
Awesome. Thanks, Alex. Hey, guys. Great to meet you all. So, today I'm going to talk to you about ZooFO Escape Match Mayhem. It's a match 3 game for mobile platforms. We've developed it in partnership with On-Chain Studios, who is the IP holder. So let's talk a little bit about the problem we had to solve. So, match 3 games, lots of levels. They are painful to make, especially when you consider you have a handful of designers that are constantly making these levels all day. There's a lot of decision fatigue and creative bias that sneaks in. I don't know if you spent all day making a match 3 board, but you tend to make the same things because your brain is just thinking about it constantly. We didn't have the budget to throw a team of 100 people on it. It just wasn't going to work for us. And to be honest with you, we needed to do it quickly. So what did we have and how could we approach this? We had 15,000 match 3 boards in our own resource from previous titles. So we're like, okay, that gives us something to work with. And we wanted to make over 2,000 game levels. Each game level has between 5 to 10 boards as part of it. So that was the problem that we had to solve. And we did make a solution. So let's take a look at the end result before we dive into how we achieved it. So, pretty cool. So generic match 3, but one cool thing was, we were able to use machine learning and Sentis to essentially save the day here, which was awesome. So, pretty much, we had a great data set of tiles, successful boards that had been handmade by our designers that followed all the design pillars that we wanted to achieve, which was awesome. What we were able to do then from this, we kind of said, right, we have this data set. Could we potentially, being Barracuda users for a long time, train a model to essentially generate a similar board set that we were used to creating? And we were able to do it. So we kind of went to the team and we said, right, how are we going to do this? So we decided that we were going to need to use some sort of noise as an input to generate our boards, which were as an output. But to do that, we essentially had to use some sort of generative model. Which one? We did not know at this point in time because there was a lot of options. So essentially, before we dive into which option that we use, let's talk a little bit about the math behind it. Very simple. Essentially, we had 2 variables. We had our variable X, which was our noisy input, just some random noise that we were going to utilize. And then we had our variable Y, which was our match 3 tile board, which was our output. So we needed to train a model to generate essentially Y given X. So pretty simple. There were 3 main approaches we could utilize. There was a generative adversarial network, also known as a GAN, and there was a diffusion approach and style transfer. Now, we essentially looked at all these options and said, well, let's try all of them because there's the only one way to find out which is best. I will say here that, many of you may be familiar with a couple of the approaches. If you've ever used like the likes of Midjourney or anything like this, we looked at all those approaches as well. And they're not that scary, to be honest with you. When you use and train things ethically on your own data set, you can actually get some awesome results. So before we could train any of the models, we had to simplify the problem into a machine learning problem space. So what we did was, essentially, we converted each of the fruits on the matchboard to a class. And each class was assigned an integer value. So if we had apples, bananas, and oranges, that would be 1, 2, 3 from an integer perspective. And then we were able, from this, to essentially train our model and pretty much simplify our data set so it was easier to ingest and train on. So from here, we dived into the various different approaches. The first approach that we utilized was a GAN. It produced great results initially. that we thought. We were like, awesome, we've solved the problem. But then as we dived into it, we realized that it wasn't actually solving our design pillar problems. It was generating boards, but they just weren't good from a gameplay perspective. They lacked symmetry and were chaotic and were just kind of random, and it just didn't make sense. So we said, okay, we now know that this is the right path that we need to go down, but this isn't the right solution. So we need to keep exploring more. So from here, we dived into the diffusion approach, which solved that chaotic problem, but it was creating too many of these island blocks where it was single, tile islands that were just essentially not going to hit all our design pillars, and they were creating a lot of no-match boards. If anyone's ever played a match 3 game, there is nothing worse when you get the board, there's no matches, and the game has to step in and say, okay, we need to replace some things. We didn't want that to happen, so the diffusion approach wasn't going to work. So we were on to our last main concept. So we were like, we hope this is the approach that's going to fit us. And it did, which was style transfer. This worked amazing. It essentially has great symmetrical results, as we can see here. We then ran a creative pass on top of that, which really enabled us to fine-tune any of those details and fit all our design pillars. And we then were able to achieve the final result we wanted to, which was awesome. I will say that with our current model, we are getting a 3% bad board rate, so essentially a no-match board, which we're expected to improve upon over the next couple of months, where with our final model, we estimate it's going to be a 1% bad board rate, which is, pretty acceptable on that side. Now, I will note, this is not a runtime solution. I think that's very important to note. This is a create time solution within the Unity editor for our design teams to utilize. So as they are editing, creating the match 3 boards, they're then saved to a JSON profile, which is then replayed at runtime, which is awesome. What we were able to achieve is we were able to self-train an image-to-image model, and we were able to get our artists to create 5,000 boards by hand, which was awesome, push that into the model, and we are now able to generate new boards at runtime and at create time as needed. I will say that the model is a little beefy. It's 37 megabytes. It's a 7-second inference time, so it takes a little bit of time, but it gives our designers all the resources that they need and ideas to create new board, new gameplay mechanics, and hit all the design pillars that we wanted to achieve. We have tested this in production. Right now we are seeing a 3x improvement in boards designed by our design team each day. So we've essentially 3x'd our power that we have on our design side, which is awesome. So it's saving us time, it's saving us money, and it's enabling us to achieve our gameplay goals as part of the project. I will say as well, this was a really cool approach because, and this wasn't part of the presentation, but we have also expanded this to other genres of games as well. And recently we just are in the creation of a bubble shooter, and we have actually used the same model for that game as well, and we're able to generate the levels also. So it's a really cool idea and concept to be able to empower your team with this, kind of Sentis side of things, to be able to generate boards and, simplify your development processes. Awesome. Thanks, everyone.
All right, you like it? Go see him. He can show you his bubble shooter. It works in WebGPU. It's pretty cool. All right, so let's dive to the last presentation. All right, so did anybody see the keynote? See the time ghost? Right? Did you notice their cloud deformation was really neat? It was really fast. Let's talk about that. All right, so what we're trying to do is we're trying to simulate the clothing on a character that's animated. So the character is animated, there's some animation, right? But the clothing is on the character. And you want very fine detail. When I'm crossing my arm, my cloth is deforming, and really fine detail. You don't want to have interpretation, and you want really very fine-grained detail. Of course, you don't want to redo your animation, so you want to keep your current animation. You just want to add the cloth deformation on top of it. Of course, you still want performance. You don't want your game running at 2 FPS, so you still got to keep it in budget. All right, so let's take one step back and let me explain a little bit how skinning works in Unity and in video games in general, just so you have an idea. So how it works is the character mesh is actually, there's a skeleton underneath with some bones. Thank you. And the bones are animated over time. So that's what animators craft when they do their animation. They're moving the bones around. And the bones will influence the vertices. Typically, all the vertex has around 4 bones influence. So all the bones influence will be linearly blended, and that will displace the vertices. All right, so if you want to add clothing animation on top of that, there's traditionally 2 approaches. One, you could do a physical animation, run some physics. That is really good. You get really like ground truth results. You get very fine detail. You don't need to redo your animation, which is a very big deal. However, it is costly. If you have a very high poly cloth, it will cost you a lot. Also, it might be slow and it might be unstable. Like if there's interpretation or there's a collider, it might blow up and explode. So you need to be careful with the stability. Another approach that is seen traditionally in games is you have a higher detail rig. So you just add more blend shapes. So that is done for, like skirts or the hair of characters. Just add more bones and you animate them over time. That works. You have very good control on per versus quality. If you put too many bones, your programmer will yell at you and say you're busting the budget, so you reduce it. You can also really fine-tune the quality. If you only care about certain hair, you just put them at a specific place and you get very good control. The problem is it's a manual setup. You need to redo your animation. You need to redo all of your animation for all the different bones, which is not that great. Also, the fine detail is hard to achieve. Like you look at here, there's a lot of bones, so it's hard to achieve very good quality. But what if you could use a neural network to do fancier blend shape for you, fancier skinning? That's exactly what they did. So you want to keep the skeleton animation. You don't want to change your animation. You keep them the same. You still have your skeleton with your bones and everything. But instead of doing the vertex skinning, you're going to run the blend shape through a neural network, which will displace the vertices of the character. Also, you want your performance to be good, right? You don't want this to be more expensive than your cloth simulation. But an AI model can actually solve all these points. All right, so first, you need to start with some training data. Neural network, you need to train on some training data. So what they did is they ran their character in a DCC tool for a bunch of different animations, for all their animation. You run through it, you run the cloth simulation. This is done offline. Let me try to play it again. Yeah, this is done offline. You use that, you bake it, you have all your fine-grained cloth simulation and animation. Then you will take a neural network and you will learn to map from the blend shape, from the bones to the vertex position. So let's see how it works. So see here on the left, you got the regular skinning. That's the linear skinning. So you're going to have interpolation. You won't have super fine cloth detail. And you might have some bulging or some joint problem. On the right, you have the Sentis deformer. Look on the leg, you can see the really fine detail, see the crease. Notice that there's no interpolation on top of the leg, and look at the bulging, how much clearer it is. All right, pretty cool, right? All right, so they did that. So I recap. Taking the input bones quaternion, you run through the model, that gives you the vertices. Pretty simple. So they did it. It works pretty well. They were getting 47 megabytes model. They were pretty happy. But then the inference time wasn't that great. Like, poke me on Slack. They were like, dude, like, why is it so slow? It's like around 1.56 milliseconds. That's okay, but it's still pretty hefty. And the scheduling CPU was 1 millisecond. That's not acceptable. So let's see how we can optimize it further. All right, so here's the black magic that happened. All of this can be done by yourself with our new functional API. So all that we did is massage the graph a little bit to be more performant. So they had a lot of branches in their model. Branching is not very good. It's doing the same operation a number of times. Actually, with neural network, it's much better to batch everything and to have like a higher dimensional tensor to do the math. All that fusing and batching save around going from 1.5 to 0.72 milliseconds. So we just reorder the graph, collapse some operation, fuse them, batch them, and it was pretty fast. For the CPU scheduling cost, a lot of Sentis users are telling me the scheduling is too slow, is eating the main thread, what can we do? Well, in this case, remember that it's doing the skinning. At the end, you want to get your everything is on the GPU, right? The bones are on the GPU. Your final mesh is going to go through a vertex shader and being shaded. Everything can stay on the same pipe. So actually, you don't need to download the vertices and then re-upload them when you're shading your mesh. Everything can stay on the same GPU pipe. Your neural network will read your bones that is in a compute buffer on the GPU. It will run the inference, compute the position of the vertices, and then your vertex shader will sample the resulting tensor and then just update the position. Also, you can use a command buffer to bake your graph, to bake the GPU code, the kernels that are being used for the inference. You bake that, and then you can re-execute that later to save on the scheduling costs. Overall, at the end, we're going to get around 0.32 millisecond CPU cost, which is pretty fine. All right, to recap. Size, 47 megabyte, pretty small. Inference GPU time, 0.72 milliseconds, pretty good. Inference CPU time, 0.3. Yeah, that's good. Final question that everybody asks all the time, the buzzkill, but does it run on mobile? So we can try it. I got this phone. It's a pretty good phone, right? But it's still a phone. I run it. So we took the scene, the character in URP, like we can't see it, like it's a small screen, but we made it run on the phone, and it runs natively. Yeah. If you want to see it, come at the booth, we'll show it. All right. All right, and that's a wrap. I hope you enjoyed it. So as Bill said, Sentis is now released. It's fully released. It's not in preview mode, so you can go and scan the QR code to get it. It's fast, free, and private. Everything stays on device. There's no cloud if you're processing audio, all that kind of stuff stays on device, no cost. You build one, deploy it everywhere. You can build on Switch, PS5, Xbox, your phone, web GPU. And yeah, if you have any question, feel free to ask us, and we'll be here to talk to you. Awesome.